So, last class we began our discussion on Monte Carlo method. This method is extremely powerful today because it uses the high computing capabilities that we have today and also the advantages of parallel computing. So, essentially Monte Carlo follows a photon from its birth to its death. That is, it goes through the path of the photon once it is emitted through the medium until it is absorbed either by the medium or by the surrounding walls. The basic Monte Carlo method has the advantage that it can deal with complex geometry, as you recall, early in the course we always dealt with simple geometry like parallel plates, cylinders and spheres. For those kinds of geometries, conventional techniques of solving a differential or integral equation is appropriate. But as you get towards a very complex geometry, it is very difficult to solve the problem by conventional methods. Monte Carlo method does not worry about the complexity of the problem. The only challenge is it takes a certain minimum time to set up the problem, and once the problem is set up, it can handle problems with very complex geometry without any difficulty. Because essentially it is a method which just follows the life of millions of photons. So, it can handle complex geometry, complex wavelength dependence, if you recall, we had shown that radiation transient gases is very complicated because there are millions of lines, and at the center of the line there is very strong absorption, and at the wing of the line there is very weak absorption. You have to take care of all this large variation absorption between the center and the wing of the line, and there are millions of them, and it is computationally very expensive. But if you follow the Monte Carlo approach, it is somewhat easier because you can deal with the absorption and emission photons in parallel. You can take many photons in the calculation, and these can be followed through in parallel. So, that is the huge advantage that these are. So, also complex angular variations. We saw that in the case of scattering, the phase function, that is the probability of a photon being scattered in a given direction, is very complex with lot of very sharp changes, and that also poses a problem in our attempt to solve it. And again, in the case of Monte Carlo, it can handle angular variation, wavelength variation, spatial variation, complex geometry, all that it can tackle quite easily once the problem is set up. As a matter of fact, in general, you think of the complexity of the problem on the x axis and the computational time in the y axis. Most problems, as it gets more and more complex, the time goes on increasing. Most conventional methods that solve integral and differential equations. As the complex one increases, the time required goes on increasing fairly rapidly, but the Monte Carlo problems are usually more like this. As the problem difficulty and complexity increases, the computational time does not increase as rapidly as it is the case with conventional methods of, that is, solving differential integral equation. So, in Monte Carlo we do not solve any differential equation, we simply follow millions of photons from its birth to its death and its various changes in direction and reflection and so on, all that is followed. So, you can see that to successfully use Monte Carlo, we need a ray tracing algorithm. So, we should be able to, in a three-dimensional geometry, see what happens if the photon leaves one surface, how it will change direction, where it will be intercepted. So, all that has to come from the ray tracing algorithm, and today there are plenty available being routinely used already for other purposes. So, this can be assumed to be available. Second, we need a random number generator. Now, this is very important in Monte Carlo, because you are going to follow millions of photons through its life, and we should take how to select these photons, which wavelength, which angle will have to be done through a random number generator. So, you need a very good quality random generator, so that when you take a sample of 1,000,000 photons, the random number generator does not repeat the numbers generated earlier. So, today again we have very powerful techniques available to ensure that the random number generator is truly random and does not repeat itself in a short number of cycles. Now, I pointed out that Monte Carlo method involves following millions of photons. Now, we might ask, how do you know that we need 1,000,000 photons and not 1,000 or 1,000,000,000? We can definitely show that Monte Carlo method will not be very good when you are dealing with 100 or 200 photons, unless the problem is very simple. As you go to more complex problems, the number of photons required will go on increasing, but how many photons do we really need to get an accurate answer is really not known a priori. So, the way you will do the problem is, so increase the number of photons gradually. Let us say you start 100 photons, then you go to 1000, then you go to 10,000 and you go to million, and find out what is the error in the result. So, this can obviously be done only in a standard problem, for which we already have a solution available from a different technique. So, you will find that as the number of photons increases, the error goes on coming down, and it will not come down smoothly. Actually, it will may show a rather behavior, and ultimately it will asymptote to a low error after about maybe 10,000 or 1,000,000 photons. And as we do in the case of checking convergence of infinite series, we go on taking more and more terms in series, and we stop when the quantity that we are interested in does not change by more than, let us say, 0.1%. So, same thing can be done here. We go on getting photons until the error comes below the value that you have set yourself. This is of course true only for a problem for which the answer is known. So, what is normally done is these Monte Carlo techniques and software that is already available is tested on some standard problems for which the results are quite well known, and based on that we make a judgment about how many photons are required in a problem for which no result is really available. That you need to do some guess. So, that you start with some assumption, you will increase double the number of photons or make it higher and see whether your results are sensitive to the number of photons. So, sensitive number of photons is a must study. You have to, so sensitive to number of photons chosen must be a standard practice in this technique, because a priori you cannot be 100% sure that your guess that 1,000,000 photons is adequate to get the result is true, especially because you must remember that you have to set your own goal for what accuracy you want, 1%, 5%, 2%, depending on the specific situation, and then guess what should be the minimum of photons required, put the number of photons and then increase the number and see whether the answer changes substantially. So, let me give an example. Suppose you want to find the shape factor, which we discussed earlier in the course using standard integration procedures. So, you start with some element here and you want to know what fraction, this is element d1 and this is surface 2, and you want to know what is fraction is leaving d1 and reaching 2. Okay. So, for a typical example, let us say this is about 1 meter and this is about 2 meters. This is a very simple problem for which a solution is available, and let us say we know the answer is 0.6396. For the simple problem we know the answer. Now, we run the same problem with Monte Carlo, and let us say we start with number of photons and then find what the Monte Carlo telling us. So, it is 100. In this case, this has been done by Professor Hubel and it is discussed in his review paper. He gets a value of 0.650. This is not bad, it is pretty close to what is obtained by an independent method. But suppose you are not satisfied, the error here is of the order of 0.01 by 0.6, about 6%. Let us say you are more ambitious, you want a more accurate answer, then you go for 1000 photons. And the answer for that comes to 0.640. This is pretty good. Here the error is 0.004 in 0.64. So, the error really has gone down substantially, but you are still not satisfied. You can go to 100,000 photons and you will get an answer something like 1695. So, this is really very accurate because the error is 0.001 in 0.6. It is remarkable. So, at least for this problem you know that you do not need 1,000,000 photons, 100,000 photons will give you an answer accurate to the 4th decimal place. But in every new problem, of course, you have to worry about how to choose that number which will give the required accuracy. This only comes by experience of doing a large number of problems. Also, you must remember when solving Monte Carlo on a computer, it requires large memory for all the ray tracing and keeping track of all the photons. and it has a large setting up time. So, since we are talking about dealing with a complex problem, the entire geometry has to be specified in 3 dimensions, so that the ray tracing can be performed. Now, just to make a point of the advantage of Monte Carlo, suppose you had a problem and we had dealt with such a problem earlier. Suppose you had 2 objects and there is a obstacle here. And you want to know what is F12. This method is very difficult to do by conventional integration techniques, and so such problems are not normally done by traditional integral evaluation. This problem is ideal for Monte Carlo, because once this 3D geometry is specified and the ray tracing algorithm are available, we just have to shoot a large number of photons and find out what fraction is able to reach surface 2. And what reaches surface 3, the obstacle, and we just have to release 10,000, 100,000 or million photons and find out how many photons are reaching surface 2, how many are reaching surface 3, and hence you can compute, for example, F12 as number of photons reaching 2 by number of photons released. This is the Fn2, provided the number of photons is very large, of the order of 10,000, 100,000 and a million. Now, suppose you have a problem, it is a large surface and a very small thing, and you want to find F12, and let us assume there is an obstacle to avoid to give you the complexity that is needed to look at such problems. Now, since surface 2 is very, very small, large number of photons will not reach it. So, most of the photons you are releasing from 1 will not reach 2. So, this will be, so releasing photon from 1 will be a very inefficient method, because most of the photons are not going to reach 2. So, this method is called the forward Monte Carlo, which involves releasing a photon and seeing where it goes, is not the best way to do it. Here, since our interest in finding out how many photons reach surface 2, is more efficient to use a backward Monte Carlo. You trace the photon backward from the place where you want to know how many photons are arrived. So, from surface 2 you trace the photon backwards and ask where it came from. So, this F12 will be number of photons reaching 2 by number coming from 1. So, you have to trace the photons from 2 back to find out how many of them must have come from 1. So, essentially the technique is same, photons reaching 2 by photons leaving 1, but here we just do not release photons from 1 and see how many reach 2. We start in photons which reach 2 and ask how many of those photons came from 1, and this is much more efficient, because not tracking all these other photons which are going all over the place, which is not of interest to you. So, quite clearly whether you use a forward Monte Carlo or a backward Monte Carlo depends on a specific application. If the application is focused on a very small region, a detector or some other object is your focus, then it is good to do a backward Monte Carlo by starting from that detector or wall which interests you and ask how many photons that reach there, where did it originate from. You trace it backwards. So, ray tracing, whether do it forward or backward, is not going to be different. Now, let us go through a typical Monte Carlo procedure to understand what happens. So, first let us think of a photon. So, as soon as you think of photon, you have to think of its wavelength, you have to think of its two angles. So, that photon has become a label. It has certain wavelength, certain angle, theta and phi. How do you find that? So, you have a random number generator, and the random generator is designed to get a random number between 0 to 1. So, these are available. You can scale any general random number generator and normalize it so that it gives only numbers between 0 and 1. Now, let us take one example. Suppose you look at a surface which emits uniformly in all directions. If that is the case, the probability of emission, the cumulative probability, as function of theta will be a linear function, because all areas are, all angles are equally probable. If it is a diffuse isotropic surface, then the cumulative probability of emission with theta will be a linear function. On the other hand, if the surface is not isotropic or diffuse, it may follow some other path. So, this is 0 to 1. So, you pick a number with 0 and 1. So, let us say it is 0.6. Then from one of these curves, depending on which surface you are in, diffuse isotropic or non, you find what is the appropriate angle, and that is the angle at which that photon emits radiation. So, fixing angle theta and phi based on the actual property of the surface as given to you can be achieved. Next come to wavelength, and you know that the fraction radiation lying in the region 0 to lambda is nothing but this all of you know this. So, this again can be shown as a cumulative probability distribution where as lambda increases from 0 to infinity, this will go like that. Now, again you pick a random number with 0 and 1, let us say it is 0.8, and for that there is a corresponding lambda. So, you have chosen what is the lambda. So, you now got a photon with a label. So, the label of the photon is, it has a certain wavelength of emission, certain theta and certain phi. Now, you go to the ray tracing algorithm and ask whether this photon is being intercepted by any object. So, let us first take an easy case of a non-participating medium. So, the photon is emitted by surface 1 and it keeps traveling, and you keep going using the ray tracing software till that photon hits another surface. So, let us say photon hits surface 2. Then you need to ask the question, is it absorbed? So, let us say the directional spectral absorptivity of that object is 0.9. So, you will take the view is that if the random number is between 0 to 0.9, it is absorbed. If it is 0.91 and 1, it is not absorbed. So, random number generator will determine whether that photon is absorbed or not absorbed. Let us say it is not absorbed. You have a random number of 0.96. So, that is not absorbed. Not absorbed, it is either transmitted or it is reflected. So, let us assume that there is no transmission. So, it is reflected. Once it is reflected, changes direction. Now, you have to give what the new direction is depending on the property of that surface. The directional properties, there is diffuse, specular or in between, and once you know that, you can determine what the angle at which it leaves by again by a random number. So, once you found the new direction, then you have to keep going until the photon is intercepted by, let us say, surface 3. Then again you have to ask using a random number whether this photon at this lambda is this absorbed by this surface. So, once the random number generates a number through which you determine whether it is absorbed or not absorbed, let us say in this case it is absorbed. So, that is the end of that photon's life. So, that photon counter is closed and the surface where it is absorbed is given that much of energy. Now, the same procedure is going to follow with millions of photons released from surface 1. So, at the end of the exercise, you will know of the million photons that you released from surface 1, what fraction reach surface 3, and thereby calculate the heat load on surface 3. So, this is the simple procedure for the Monte Carlo for an enclosure in which there is no medium. So, this is very simple, and in many situations people write their own software to calculate a shape factor using Monte Carlo. But when you deal with a participating medium, life gets a little more complicated. So, the photon leaving surface 1 is entering a gas, let us say, which is absorbing and scattering. So, as soon as photon leaves surface 1, you have to decide how far will it go. So, you have to find a photon mean free path. This could be taken as 1 over a lambda, for example. So, once you know the distance, again as the photon leaves surface, you keep generating random numbers to decide whether that photon is indeed absorbed or is scattered. So, absorbed, again the story is over. You have just keep count of this energy being gained by that surface. So, that would conclude that photon's life. So, you go back and pick another photon. Now, if the photon is not absorbed, then it is scattered. So, that is now a new story. Radiation came from some place and hit a particle, and that particle does not allow the photon to be absorbed. It reflects in some other direction, and you have to know what direction it has, what direction has it reflected. So, that also has to be determined by random number generator. You generate another random number, ask yourself what is the probability the photon is scattered and not absorbed. So, in this simple problem in which the sphere is opaque, one can safely say that if it is not being absorbed, then it is scattered, and the angle which is scattered depends on the refractory properties of that surface. Once it is scattered, again you keep following it until it hits another photon, and it may be absorbed again or may be reflected. So, this sequential event goes on. Although the procedure looks very long and tedious in terms of setting up the property data and then the ray tracing software and interpolation result, remember that this is the only problem, only methodology available to us to deal with complex geometries, complex surface properties, steady surfaces, surfaces with very rapid change in wavelength. Such surfaces cannot be dealt easily by traditional method like discrete Rodian method or simple harmonic method. A lot more methods are there, but they do get a bit difficult and the problem is somewhat complicated. Now, a number of techniques are now available, number of software available to perform all these actions without the need for writing any specific Monte Carlo code, because standard codes are available, you just merely have to get access to it and you calculate the amount of radiation absorbed in any one surface given emission from a surface, gas interaction and finally reaching some surface. Now, we mentioned that typically solar radiation that is emitted has of the order of 10 to the 15 photons. So, you might wonder why people make do with a million photons. The answer to that depends really on your sampling strategy. As most of us know today, in many areas, whether it is consumer preference or whether it is the voting pattern in democracy, is determined by a sample survey. And depending on your particular problem, you should be able to judge what fraction of the total photon that are emitted is enough to determine the property that you want. So, although it is desirable that we release 10 to the power 15 photons, it is not necessary, because after a certain number of photons the results will stabilize and you may get the requisite accuracy after doing a million photons with a truly reliable random number generator. So, that is the message that we have to take from various examples that we have seen in the literature. Now, we will not discuss specific details of the way the Monte Carlo technique, within it there are various ways to accelerate the process of ray tracing or determining the fate of the photon. We will not go into those details, but we should point out that although Monte Carlo is undoubtedly far superior to other techniques for complex geometries, one consequence of using this kind of technique is it is not easy to determine what is the total error in your computation. It requires a lot of testing, a lot of expertise being built up by running a code for many cases to decide under what condition you need a billion photons, and when you can make do with 100,000 photons, or when you may require 10 million photons. That cannot be specified a priori, it has determined by trial and error, and as you get more expertise in running a code and getting the answer more or less right, if that expertise can be obtained in a short time, then you can easily use Monte Carlo for a number of applications. But before using every application, one has to ensure that for that application there is sufficient number of photons has been used. And as I said, there is no simple thumb rule to tell you whether a million photons is adequate. So, if you look at a complex geometric problem, generally if you look at the literature, they all show that Monte Carlo is far superior to, let us say, what we discussed in the last lecture, the discrete ordinate method. So, very examples done in literature for real life examples like boilers, glass tank furnaces, and such examples, they all demonstrate that in real life complex geometries that you encounter in engineering applications, Monte Carlo is generally superior to all the other techniques discussed in this lectures, that is discrete ordinate, experimental kernel approximation, maybe a finite volume method. So, as long as the geometry is complex, Monte Carlo always has an advantage over traditional methods. But the decision to use Monte Carlo must be based on how often you have to do your simulation. Now, as pointed earlier, the real difficulty in Monte Carlo is the need for setting up the problem for a given geometry. Now, that will take a minimum amount of time, and if that takes a large amount of time, and after doing that you are going to do only one simulation, then surely it is not a very effective use of Monte Carlo. So, Monte Carlo should be used in situations where you need a large number of simulations under a variety of conditions, and if that is required, then it makes sense to spend sufficient time and effort to set up the problem and do a lot of validation, and then we are ready to do the full simulation for a variety of situations. The other thing that must remember is that in a participating medium, like a gas or particles, the CPU time required will depend on optical depth. So, optical depth increases, you will find that CPU time will go on increasing, and this is very easy to understand as long as you have a gaseous medium which is absorbing, scattering and emitting radiation. If it is optically thin medium, it is hardly absorbing scattering. So, the number of events that you will see inside the enclosure will be small. Most of the photons will leave one wall and reach another wall without much change in direction or loss of photon. So, in such situations, the Monte Carlo simulation can be done very rapidly with a few number of photons. But if there is strong absorption, emission and scattering in the medium, then there are large number of events that you have to simulate, and you necessarily need to use a large number of photons, and naturally it will take you more time to do the computation. So, this issue has to be kept in mind in taking up a particular problem for Monte Carlo. But it is quite clear that in the future most radiation heat transfer problems will be done through Monte Carlo, and this is going to happen because better software will be developed in the coming years. The computers are going to get faster and less expensive, and all that means is that the desire of engineers to solve complex problems can be met, and hence the use of Monte Carlo will become more and more common, and already there are books in radiation heat transfer which comes along with a CD containing a Monte Carlo software. And even in teaching, one will see Monte Carlo being used as a simulation package for students to understand radiation heat transfer. Because the traditional method of solving engineering problems was set up the basic equations in a differential integral form and then integrate the equation with traditional techniques. But if finally the industry is going to solve most of the problems using Monte Carlo, then there is not much merit in teaching students to solve these problems by traditional techniques of solving differential integral equations. It may be better that students gets the familiarity and the confidence in using the Monte Carlo software to solve fairly difficult problems in the class and learn about the complex behavior of radiation transfer through doing a large number of simulations using Monte Carlo code. Now, the reason why I am saying this is this kind of thinking is already prevalent in fluid mechanics, where earlier we learnt about the behavior of fluid flow in complex geometries by going to the laboratory and using a wind tunnel or water tunnel to see what kind of flow patterns are created in real world. But today that work can be done by numerical simulation in a very short time and in a very cost effective way. So, the need to go to the laboratory to learn about how fluid flows is becoming less and less. To give an example from the aeronautical industry, the first aircraft which was designed and flown by Wright brothers had no simulation. Everything was done by the Wright brothers using their practical knowledge about control, about what makes an aircraft fly, and everything was done empirically, everything was done in practice, nothing was done in simulation. But if you look at the most recent aircraft which is being released in the market, you will find that a large fraction of the money and the effort in designing a modern aircraft goes in simulation, because simulation is very good to tell you about the flaws in the design or give you an insight about better design. So, that is why the industry prefers to use simulation packages if they are easy to run, and learn from that what geometry, what conditions will make it easier. But of course, finally after all the design over, you need to test things out. So, you need ultimately some kind of internal to verify your computer simulation, but most of the work is done through computer simulation, and this is now becoming more and more common in radiation heat transfer also. So, although Monte Carlo has not completely superseded traditional techniques to solve radiation problems, but we believe that this will occur in the next few decades because of the power of Monte Carlo to solve any complex problem. And the challenge of setting up the problem quickly has to be met, and I do expect better software to become available, so that the user can set up the problem very quickly, and once that hurdle is crossed, you will find Monte Carlo being used in classrooms, in industry and any other place, because it has the promise of being able to solve the most complex problems, three-dimensional problems that we normally encounter in radiation heat transfer in engineering. So, problems like boilers, complex concentrating solar collectors, flow through radiation through fibrous media, all these kinds of problems which are three-dimensional, complex geometry, lot of scattering, cannot be solved with many of the conventional techniques that we have discussed in these lectures. But certain aspects of these lectures will not become irrelevant, although in practice Monte Carlo will become more and more common. But to get a physical insight into the way radiation behaves, it is necessary to solve a few problems using the conventional techniques, so that you get a physical feel for how radiation heat transfer results behave. We saw a large number of examples in this course in which we use traditional techniques only, about the behavior of a photon being similar to that of a fluid undergoing conduction, provided that the photon mean field path was small compared to the length scale of the problem. And similarly, we saw that when you have very small photon mean field path in a gas, you can use a differential approximation to solve these problems. So, when you look at a solution to a complex problem through Monte Carlo, various smaller parts of the system, their behavior one should be able to qualitatively think about its behavior and be related to simple solutions during the class. So, although all practical problems will be ultimately solved in Monte Carlo, the physical intuition that is necessary to design complex systems comes only by simple techniques that people use to solve problems. So, although we ultimately desire to solve three-dimensional problems of relevance to industry, we still can use the results from very simple and idealized geometries like flat plate, cylindrical or spherical. Those are necessary in order to get a feel for the real world, but the real world problems all solved in Monte Carlo. But once the results come out, you should be able to judge whether this results really makes sense or not, and that intuition can be gained primarily by solving some simpler problems, or also of course by doing a large number of simulations using Monte Carlo. Over a period of time, an intelligent student will get a grasp of why a certain pattern of behavior is seen in certain problems. So, although a certain technique will ultimately dominate in view of its advantage in dealing with complex problems, still some of the simple problems of semi-infinite plate or infinite cylinder or a symmetric sphere all those cases that were discussed in the lectures are not real world problems. They are idealized problems that we did in order to get some feel for how the real problem should behave. So that when the simulation computer are obtained and the graphics are generated, you should be able to judge whether the answer looks right or wrong, and that can be primarily be done only through these simpler problems we have dealt with in this course, which are not really directly relevant to industry settings. So, now with that we close our discussion on Monte Carlo, and the best way to learn Monte Carlo is to really solve a large number of problems with the Monte Carlo package and get a feel for the way Monte Carlo behaves in practice. Now, we move on to a couple of other small topics which we had not completely covered in earlier part of the course, and one of them we started out is the radiation detectors. We had briefly covered it in one of the lectures, but had not gone through the complete. Now, there are two major types of detectors we had pointed out. One is thermal, that is the radiation absorbed by the detector causes a temperature change, and that leads to a property change which can be measured. Now, the more common kinds of detectors that are now coming into the market, which are getting very popular, are based on quantum effects. So, in a thermal detector, you are converting photon to heat and hence temperature, and that temperature change can be directly measured, or you can look at the change in resistance or capacitance or inductance induced by the temperature change. So, a large number of detectors exist today for measuring radiation by merely allowing the radiation to impinge on an object, be absorbed, and the temperature rise is proportional to the incoming radiation. But the more popular ones which are now coming to the market are really the quantum detectors, which convert a photon ultimately to an electron. So, this is a much more elegant detection method, because it can be much more accurate, because you are letting each photon induce a change in the sensor which causes an electron, one or more electrons to be released. So, this technique of course will be very sensitive, because it measures one photon at a time. Now, the advantage of this is that suppose you have a very weak source of radiation, like an example I can give is detection of fires. Now, today forest fires are being detected, or even man-made fires detected by satellites. Now, the amount of radiation from a forest fire, a small forest fire, reaching the satellite is quite small. Typically, satellites are at 800 kilometers or even larger height, and so the amount of photons reaching there is very small. Still these modern sensors are able to detect them, because in these detectors a photon that is impinging on the sensor releases electron, and this electron is accelerated now by electric field. So, that is high energy, then it hits another detector, and for each electron that comes out here, 10 more electrons are released from another detector, and you can multiply this many times. So, if each time number of photons increase 10 times and you do this 10 times, you get 10 to the power of 10 amplification. So, such large amplification means that you can detect very low levels of radiation coming from forest fire pretty accurately, and this has been used by NASA to map the world fire zones, and so this has come very useful to understand which are parts of the world are being destroyed or being converted through natural forest fires or man-made fires. So, this shows that detectors which are very sensitive are very useful, because they enable to detect very small signals. So, we will continue this discussion in the next lecture.